This is the 14th group of slides. On this lecture, we will talk about thermal analysis. Thermal analysis is the term applied to a group of method or techniques where the physical properties of a sample are measured as a function of temperature or time. In this particular lecture, we're going to restrict our discussion to two types of that technique, which is TGA, thermogravimetric analysis, and DSC, differential scanning calorimetry. A couple of references, you can read those on your own. This slide is just a table of main thermal analysis methods. As I said previously, we'll discuss or limit our discussion to TGA and DSC. Another slide. Just probably worth a quick rehash of some basic thermodynamics. Everyone should be familiar with the Gibbs-Helmholtz expression where delta G is equal to delta H minus the temperature times the entropy of a system. We all should know that general chemical reactions move forward. If delta G is less than 0, they move forward spontaneously. If delta G is 0, then it's at equilibrium, and a reaction does not occur if delta G is greater than 0. Thermal analysis obviously involves the monitoring of temperature and mass during spontaneous reactions. Just to develop some basic relationships, we can differentiate the Gibbs-Helmholtz equation with respect to temperature. So if we take d delta G as a function of dt, it equals negative delta S. And that allows us to show how we move from a stable situation to one where a reaction will occur. If delta S is greater than 0, then an increase in the temperature will cause delta G to be less than 0 and a reaction will go forward. Alternately, if delta S is less than 0, decreasing the temperature will achieve the desired spontaneous reaction, because then delta G will be less than 0. Once a reaction is made to occur, a thermal analysis may be used to detect the process and provide the information going on in that process. Thermogravimetry, which is the first technique we'll talk about, is the study of weight changes of a specimen as a function of temperature. All right, this technique is used strictly for transformations involving the absorption or evolution of gases from a specimen consisting of some kind of a condensed or solid phase. It's achieved by plotting a mass versus temperature plot. And as we, in the first bullet, already established, that this is pretty much for the decomposition and in some cases oxidation of a sample. Measurements of the changes in sample mass are made using a thermobalance while simultaneously in a predictable manner increasing the temperature. Sometimes this balance is enclosed in some kind of a closed system so that we can control the atmosphere. General consideration: suitable samples for TGA are solids that undergo one of two types of general reactions. They're either reactants that result in some kind of a reaction product plus a gas, and of course in TGA that will manifest itself as a mass loss, or we get some kind of a gas plus a reactant to form an ending product, which is a mass gain. So in that case, that would be like the oxidation of the metal. Processes occurring without a change in mass, i.e. the melting of a sample, cannot be studied by TG. Correspondingly, something like the melting of a sample would be measured by DSC, which we'll talk about later on in these slides. So first we'll talk a little bit about instrumentation. I won't spend a lot of time on it because for the most part you would just go off and use the TGA system that is bought from one of the many manufacturers that produce these things. But the basics of thermogravimetric instrumentation include several basic components consisting of a microbalance, some kind of a heating device, a unit for temperature measurement and control, a means for automatically recording the mass and temperature changes, and then some kind of a system to control the atmosphere surrounding the sample. And here's just a schematic of a couple of typical diagrams of a thermal balance. On the left, you basically have some kind of a wire that's on some kind of a balance point. You have a position transducer on the right, and it basically measures the position of the sample in the furnace. And of course, there's a corresponding counterweight. On the right side is a mechanical version of the same kind of process. Balances must remain in precise and accurate continuously under extreme temperature and atmospheric conditions. And they need to deliver a signal suitable for recording. Null deflection weighing mechanisms are generally favored in TG because they ensure that the sample remains in the same zone of the furnace, irrespective of changes in the mass. So you want something that measures the deflection and then either compensates for it or measures the force as a change of the weight. Because if the sample actually moves up and down in the furnace zone, there can be changes in buoyancies from the gas, and there also can be changes in the actual temperatures. There could be a temperature gradient within the furnace. So in general, in a TGA system, a null deflection device is preferred because it maintains the sample position in the furnace. The balance must be sensitive enough to detect the changes in sample mass, and that typically is considered at least 1 microgram. For a 1 gram maximum load balance. The output weight signal may be differentiated electronically to give derivative TGA curves, which are used to help analyze the TGA curves. The heating chamber. The furnace is normally an electrical resistive heater, okay? However, it should be non-inductively wound. That's because you don't want to create any kind of magnetic moment inside the heating chamber, which could affect the sample weight. It should be capable of reaching 1 to 200 degrees above the maximum desired working temperature. Most TGAs have a maximum operating temperature of about 1,000 to 1,200 degrees centigrade. They need to have a uniform hot zone of reasonable length, especially if it is not a null deflection balance. They should reach the starting temperature as quickly as possible. That's to prevent mass losses while you're actually heating it to your starting point. And you want some kind of a system where it does not affect the balance mechanism through radiation or convection. In other words, as that heat is rising within the hot zone, you don't want that actually affecting the sample weight. In some more exotic systems, microwave and infrared radiation has been used. I've never personally used one or been exposed to one. There are several different types of time temperature programs that people use in TGA. The most common is a constant heating rate, where the temperature is just increased at some fixed ramp rate while you measure the corresponding weight. There's also isothermic temperature control and quasi-isothermic temperature control. That's a situation where you bring the furnace to a specified temperature and then hold it at that temperature and measure the weight during that hold. Quasi-isothermic means that you're basically varying those isothermic holds. And then correspondingly, you can do a gradual rise with holds at the same time. All right, so it's kind of a combination of a constant heating rate and isothermic temperature control. And then there are temperature time cycles and constant speed of reaction cycles. These are generally, they're kind of more exotic techniques, but for 95% of the work you'll ever do with a TGA, you would just do a constant heating rate temperature time program. And then you can see in the plot below, there's the heating of a furnace with a constant heating rate, right? And you have a plot which is just a straight line with a temperature on the y-axis and time on the x-axis, and it's just a straight line with some slope beta, which is the heating rate. The speed at which you actually increase the temperature will affect the results. There is a lag between the sample temperature and the furnace temperature. So during the heating, the temperature difference there will be a temperature difference between the furnace and the sample. The faster that you heat a sample, the larger that lag will be. On the right plot is a plot of the change in the heat as a function of the change in the temperature, plotted against the actual temperature itself. And you can see that that dQ dt peak is much larger when the heating is the fastest, right? So you get a substantially, a large increase in this dQ dt value when you heat fast. What does that mean? It means generally in the TGA curve, you want to heat as slowly as possible. But obviously if you're doing a TGA curve and starting from 30 degrees centigrade and going to 1000 degrees centigrade, if you're doing it at 1 degree a minute, that would be a 970 minute scan. typical or kind of a common ramp rate in TGA is generally 10 degrees to 20 degrees a minute. This is what I just said. Thermal equilibrium is better reached by a gradual raise of the temperature. And then here's just an example of a gradual raise of different type of step programs. So in the top left is an example of an isochrone isothermal or thermic analysis. So the time intervals are fixed and you hold it at some fixed temp for a fixed time. On the right side is a quasi-isotherm, right? So once again, you get to a temp, you ramp up to a temp, you hold at that temp for some time, then you ramp up to another temp, hold at that time, and so forth. You can also do controlled heating and cooling, and that's what the plot would look like there in the lower left. And then there's controlled heating and cooling. You can do whatever kind of really exotic heating and cooling program that you want to do. The atmosphere is actually important in TGA analysis. The sample reaction will depend on the gases that are present of it in the reaction. The most common atmospheres of TGA are generally either air or nitrogen, but people can do it with argon, people can do it with CO2, but understanding the reaction that may or may not occur with depending on the gas that you choose is important to understand. It's also important to understand, though, that changing the gas actually changes the heat conductivity in the TGA. So something like argon, which can conduct heat better than something like air, well, will change the rate at which the heat is transferred to the sample. Additionally, changing gases will affect buoyancy and current effects. Because as you heat the gas, the density of the gas changes, which causes a buoyancy impact on the sample. So the sample will appear to change weight as the buoyancy changes inside. As the note on the bottom of this slide says, for all thermoanalytical investigations, it's important to report the type, pressure, and flow rate of the gases used in the experiment. So what that means is any technical report that I would do in my lab for TGA, I would have a parameters table where I basically say, gas used, air, pressure, or flow rate. You really wouldn't have both. You might have a flow rate of X number of milliliters per minute or something like that. So here's an example of why the choice of gas matters in the TGA curve. So here's the proposed TGA of calcium carbonate in 3 different atmospheres. And you'll see that the first plot is shown in vacuum and that the decomposition temperature occurs at about 500 degrees. You change the gas to air, right, which will actually slow down the reaction rate and reaction temperature, increases the reaction temp to about 750 degrees. Then as you change the gas to carbon dioxide, you increase the temperature of decomposition up to closer to 1,000 degrees. That's because the partial pressure of CO2 is much higher in that circumstance, right? And so the CO2 won't evolve as quickly. So the choice of gas matters. Now I want to talk a little bit about the sample itself in a TGA. The sample form, defect content, porosity, surface properties, and so forth all influence the behavior on heating. For example, a single crystal sample gives a different response than a powdered sample. And in the case of a single crystal, you have a single thermal mass, which is going to get heated from the outside in. So it will actually slow the reaction in a particular case like that, whereas a powdered sample will hopefully, the heat transfer through the sample will be quicker and provide a more uniform reaction. Large sample sizes cause problems like heat transfer and gas exchange with the surrounding area. If you have a very large sample size, kind of like a single crystal, you have a large thermal mass that's going to heat from the outside in and slow the reaction. Correspondingly, you may have reaction products that also slow down the reactions by increasing localized partial pressures and changing the reaction rate. So in general, a small sample size is preferred. Approximately 20 milligrams is a good sample size. When dealing with pharmaceuticals, which are very, very low density, a typical sample size will be as small as 5 milligrams. Obviously, you have to have a balance that's sensitive enough to do this. In general, samples should be a very fine powder, and then spread thinly and uniformly in the TGA container. Here's an example of some of the crucibles that are used. Crucibles are available in all kinds of materials, ranging from silica to alumina, platinum, gold, and so forth. I think for the most part, most people use platinum crucibles because they have a very high max working temperature. You know, as this thing says, max working temperature up to 1600 degrees C, and they're non-reactive. The problem with platinum crucibles is they're very expensive, and TGA pans are actually very small, so they're damaged relatively easily. So you can spend a lot of money on platinum crucibles, but that's generally the preferred type of sample. And obviously you want to make sure you're selecting a crucible that will not react with the sample itself. And now here's an example of the decomposition temperatures of calcium carbonate as a function of the actual crucibles that you may or may not select. So in plot number 1, you have an open crucible with a very large surface. So basically you're exposing a large, so the crucible is wide open, you're exposing a large amount of the sample to the heat and the atmosphere of the TGA instrument, and that the reaction temp is actually at a lower temperature. As you go to a smaller yet open crucible, you'll raise the reaction temperature, and then in the third case, if you actually put a lid of some type on the crucible, you will increase the reaction temperatures because you're creating a localized partial pressure of the evolved gases. So the crucible matters. In general, in TGA though, it's generally just some type of an open pan or open crucible. Now we're going to talk a little bit about the calibration of a TGA, the temperature calibration. Platinum thermometers, resistant thermometers, or thermocouples are typically used for temperature measurement. Large differences between the sample temp and furnace temp can exist, so some kind of a calibration is absolutely necessary. If you're doing work in vacuum or in a fast flowing atmosphere, this difference can be even higher. The temperature calibration for a small furnace can actually be done in one of a couple of ways. One, you can take advantage of the melting point of certain metals. To do this, a series of metal wires are actually hung from the same mechanism that you would typically hang the sample pan. You can see this in the diagram to the right. So you have the hanger where the sample pan would be, and then you hang some different metal wires from it. And then you slowly raise the furnace temperature, and then you'll get to a particular point where that wire melts, okay, would come off the wire and would result in a substantial weight loss that you could record. And by having a series of these wires, and the example in the slide, of course, is indium, lead, and zinc, and you can look at the various temperatures, would give you some kind of a calibration curve that you could use for calibrating your instrument. I don't think this technique is really used too much anymore because it obviously results in this metal melting and then going to the bottom of the furnace system. And in most small systems, you wouldn't want to dirty up the inside of the system doing it, but it is a way of doing it. Correspondingly, it can also be done by checking the Curie temperature of certain metals. For those that the Curie temperature is the temperature point where a material goes from ferromagnetic to being paramagnetic and results in a sharp weight change. So how you would do this is in the furnace, you would basically put a small amount of a metal, and then here's some examples off to the right. So say a piece of nickel in the TGA pan, and then you might put a magnet underneath the pan. By slowly heating it to the Curie temperature, suddenly it is going to go from ferromagnetic to paramagnetic, and a very dramatic weight change will suddenly occur as it loses its magnetic properties. So that magnet initially is pulling it down, giving it the appearance of a much higher mass than it really has. And then when you change those magnetic properties, that mass is going to suddenly drop substantially. And then this is the way I actually calibrate the TGA in my lab. We should talk a little bit about the interpretation of TG and DTG curves. DTG curves are derivative TG curves. In this particular case, there aren't actually DTG curves on this diagram, but these various plots that you see on the left are what you would typically see in a TGA scan. So to go right down the list, the line labeled 1 is basically where the mass does not change as a function of temperature. And all that means is that the sample is undergoing no decomposition, no loss of volatiles. There's no weight change. However, it should be pointed out that you could go through a phase transformation, and a phase transformation that does not involve sublimation, meaning being converted to a gas, will not really be picked up by TGA. And we'll talk about DSC, which is you'd see where you would see a solid phase transformation. Curve number 2 is an example of an initial rapid mass loss, and this is characteristic of desorption or drying. So this is typical of just like adsorbed moisture on a sample. And as the bullet point indicates, if this is true, then rerunning of the sample immediately after, before moisture reabsorbs to the sample, should result in a flat line. And you almost always see this in the beginning of TGA curves if you haven't actually dried the sample prior to doing it. Number 3 is an example of a single stage decomposition, I'm sorry. So the calcium carbonate curves. So CaCO3 decomposes into CaO and CO2. That would be a single step decomposition. The step function shown in number 4 is a multi-stage decomposition with relatively stable intermediates. So that basically means that there's not a lot of overlap of the various decomposition stages, and that between decomposition stages, the reactants are relatively stable. Number 5 is an example of multi-stage decomposition with no stable intermediate products. So in essence, these decompositions are overlapping. This is something that you might be able to correct for by changing the heating rate. So slowing down the heating rate might allow the decomposition to be more clear. Number 6 is an example of a gain in mass due to some kind of reaction in the atmosphere. This is typical of the oxidation of metals. Okay. And then number 7 is the example of an oxidation product that then decomposes again at higher temperature. This slide shows a few things you might want to think about before actually starting a TGA measurement. It's useful to have an exact characterization of the starting materials, i.e. the purity of the sample, the grain size. This is something that would be great in an ideal world, right? So you have a sample, you run off to a particle size analyzer, examine the particle size, and so forth. This is not always something you really are able to do, but if you have access to that information, it might help you diagnose issues that you run into during your TGA analysis. It's always useful to have large amounts of starting material in case you want to repeat the experiments and do further measurements. It's a good idea to remove absorbed water by drying. So delta M must be constant. We just talked about that on one of the previous slides, where you have a that initial loss of mass from drying. And this is because adsorbed water or absorbed water can actually vary quite a bit because of the conditions of the lab, the humidity on the particular day, the sample size. So a lot of people, as part of TGA analysis, will dry a sample in a drying oven at 60, 80, 100 degrees C before actually running their TGA. And that way they get sort of repeatable results. It's very useful to use samples that have a narrow grain size distribution. The reason for that is again, you get consistent reaction during the TGA process as opposed to reactions being slower in one part of the sample and faster in others. For measurements that are going to be done in vacuum, you generally want to have samples that do not have grain sizes below a 60 mesh size, which is actually fairly large, 0.25 millimeters, but the reason for that is the sample can actually waft out of the sample pan, which 1, contaminates the system, and then 2, of course, shows up as a loss in sample weight. So here's an example of an application of TGA. This is only for studying thermal events accompanied by a mass change. So in this particular example, on the left-hand side, we see a TGA curve of a copper sulfate pentahydrate. So it maintains a constant mass up to about 100 degrees, and it loses 2 of its waters in its first step. And then that step, continues all the way down to just under 200 degrees. So it achieves an equilibrium where it's now a copper sulfate with 3 waters attached to it. We get to about 250 degrees and we see the next step where it loses mass. And then it's relatively stable for a short period of time as the temperature increases. And it becomes copper sulfate with a single water. And then ultimately at about 350 degrees, we lose all of the waters and it, just resulting in copper sulfate. Theoretically, you should be able to correlate the mass losses to the calculated or theoretical mass loss based on the chemical formulas of the compounds. The curve on the right is an example of this same reaction under different partial pressures of water vapor. So you can see in the first curve on the left at 20 millimeters of mercury, the onset point of the decomposition of calcium sulfate with 2 waters is at about 83 degrees. If we increase the partial pressure to 120 millimeters of mercury, it increases to 125. And then if we go to 600 millimeters of mercury, the onset temp is about 136 degrees. So the higher the partial pressure, the higher the decomposition temperature. And then of course, correspondingly, the lower the partial pressure, the lower the decomposition temperature will be. The TGA can actually be very useful in terms of understanding the thermal stability of a lot of common samples, such as the hazards of storing explosive. It's used a lot for understanding the shelf life of drugs, right? So if you were to, look at the TGA curves of a particular drug product, you can tell at what point that starts to break down. If its decomposition temperature is fairly low, then you know that storing that pharmaceutical product in a high temperature environment, even a desert type environment, could affect the stability of the drug. TGA curves can also be used for fingerprinting purposes. So sort of like X-ray diffraction, they may have a certain overall look to the curve that you can kind of match and be comfortable that what you have is, what you're hoping to have. And then the thermal balance in a TGA can also be used to measure the vapor pressure of samples and magnetic susceptibility and things like that. When you're actually looking at a TG curve, there's really a few things you really should consider. One is just the overall shape of the curve. Are the steps well defined and reach equilibrium points? Do they overlap? Is it continuously downward sloping and so forth? You want to note the particular temperatures at which changes in mass occur. All right. This can be severely affected by many experimental conditions, especially the ramp rate when you're actually heating your sample. And obviously the gas, the atmosphere in the TGA. And then you also want to note the magnitudes of mass changes, because these magnitudes can actually be directly related to the specific stoichiometry of reactions, and you should be able to actually calculate the quantities based on these reactions. So here's kind of an example of this, an analytical calculation. Under controlled and reproducible conditions, quantitative data can be extracted from most TG curves. Most commonly, the mass change is related to a sample purity or composition. So in other words, you can take a TGA curve and check the purity of something by comparing the observed mass change and the calculated mass change based on a particular reaction. So for example, let's say we have a compound that we've run a TGA curve on. That compound may be either magnesium oxide, magnesium carbonate, or some kind of magnesium oxalate. A thermogram of the substance shows a loss of 91 milligrams from a starting mass of 175 milligrams. And you ask yourself, what is the formula of this compound? And then first you consider the relevant reactions that may or may not be the case, right? If it's MgO and we heat this, we would get no reaction because MgO is stable to very high temps. If we have magnesium carbonate, at some point that magnesium carbonate will decompose into magnesium oxide and carbon dioxide. In the case of an oxalate, it'll actually have a two-step function where it decomposes, first loses the CO2. I may have that backwards. It may lose the CO and then lose the CO2. I'm not really sure of the order of the reaction. I actually think there's an example of this in the future. But in any case, the point of the slide is we can calculate the mass loss of the sample, right? So we have 91 milligrams of mass loss over 175 milligrams of starting mass, which is a 52% mass loss. And if we go through and calculate the mass loss of the various reactions, we see that the calculated mass loss of magnesium carbonate is 52.2%, where the calculated mass loss of magnesium oxalate is 64.1%. So based on this calculation, we can thus conclude that the compound present is magnesium carbonate. So this is just a relatively easy example of the calculation. And okay, here's an example of a calcium oxalate, not a magnesium oxalate, and it just shows the TGA curves and derivative TGA curves of calcium oxalate. And you can see the various steps that happen. So you see it's relatively flat in the beginning, and then at what appears to be about 100 degrees, maybe 125 degrees, we get the initial loss of the 1-water. So this is calcium oxalate monohydrate. And the 1-water comes off in that first step. And then it achieves an equilibrium and remains relatively flat till it gets to about 400 degrees. And we see that the calcium oxalate without the water now decomposes into calcium carbonate and carbon monoxide. Reaches another relative equilibrium and then decomposes starting at, 650 degrees from calcium carbonate to calcium oxide and carbon dioxide. And then there's a small table on the right where I've actually gone through and calculated the theoretical weight loss versus the actual measured weight loss based on these curves. So you can see that it's when you're dealing with relatively pure compounds, you can actually use this to, one, measure the purity of the compound, but also verify what the compound is. If you're running TGA and you don't know what it is, something you can actually utilize is what they refer to as evolved gas analysis. Evolved gas analysis is typically where you either hook up a mass spec or an FTIR to the evolved gas. So the gas that's coming off the TGA goes through the mass spec or the FTIR and you measure its signal. In the example below, the TGA curve is the solid dark line in there, and then superimposed on it is the mass current plot taken from a mass spec. And then you can see at roughly 200 degrees, that's representative of the mass of water. And then you see another step at about 500 degrees, and that corresponds to the mass current that would tie to carbon monoxide. And then at 700 to 800 degrees, you see another peak, which corresponds to the mass current of carbon dioxide. So if you have no idea what it is you're analyzing, you can at least use something like this to try to identify what it is that's coming off, and then maybe work backwards to understanding what it is that what kind of sample that you have. Now we're going to talk about DSC, or differential scanning calorimetry. In power compensated DSC, the sample and a reference material are maintained at the same temperature throughout some kind of a controlled temperature program. So basically you have two independent heating loops. One is the sample itself and one is a reference material. And what you do is you actually maintain them at the same temperature, but measure the difference in the energy that's required to maintain them at the same temperature. All right. You have to kind of think about that a little bit. It's not necessarily straightforward, but depending on the material in the sample, it will require more or less energy to maintain that temperature than our reference material. And by measuring that difference, we can identify what's going on inside of it, whether a melting event is occurring, a crystallization event, depending on whether heat is flowing into it or heat is flowing out of it. DSC has a broad application. It can be used in the study of heats of reaction, kinetics, heat capacities. It can be used to develop phase diagrams, determining thermal stability, sample composition, and so forth. Not going to really talk about this diagram too much. I don't think there's really any point. As I said on the previous slide, you basically have two separate heating circuits, right? One heats the sample, one heats the reference, and you monitor the difference. Thermal events in DSC show up as a deviation from the DSC baseline. The DSC baseline is basically that permanent difference between the energy required to heat the sample and heat the reference. We show it in a DSC curve as what's typically a relatively flat line. So that's the DSC baseline, and any kind of an endo or exothermic event shows up as a deviation from this baseline. Typically, and the first thing I'm going to do is actually fix this slide because it's actually really bad. It's got something I disagree with. On this slide, it says in DSC, endothermic responses are usually represented as being positive or above the baseline. That's actually not really a true statement. It might have been true at one point in time. Generally, what they do is, depending on the software and who makes it, you can actually orient the plots any way you want. And so when you look at the plot, somewhere on the plot, it will be marked as exothermic up or exothermic down. So they'll typically say something like this. Bear with me, my wonderful art skills again. And they'll mark the plot like that. So it'll indicate on the plot exothermic up, exothermic down. So in this particular DSC plot, it's exothermic up. This is the DSC trace of PET, looks like it's PET, some kind of PET copolymer. I'm not really familiar with what it is. But so we start with some kind of a hysteresis peak. The initial drop or use of energy is the TG temperature of the PET, all right, followed by hysteresis from that TG. And then the first exotherm, so that's an exotherm. That's actually the temperature of crystallization right there, the peak of that exotherm. So exothermic events are generally crystallization events, right, where you're actually putting off heat to form that crystal structure. Then as we move down the DSC curve, we get to an endotherm. And I think we've actually asked this before. What is melting? Is melting exothermic and endothermic? Obviously, by exclusion, we know that melting is endothermic. So we have glass transition in the beginning, followed by crystallization, followed by melting. So this is a typical DSC curve. It's just important that when you look at a DSC curve, you look on the plot to understand whether it's oriented exotherm up or exotherm down. This is just a schematic of a sample chamber, not really relevant. This slide talks a little bit about the type of sample pans you might use. For DSC, less than 500 degrees of sample pans are usually just aluminum sample pans, which are sealed by crimping a lid into it. It also indicates cold welding for volatile samples. I think that's old. I don't think people really cold weld anymore. They do actually make hermetically sealed pan lids, and you use a little press to actually seal that lid in. But kind of like TGA, sample containers can be made of other things. If you're going to go at temperatures above 500 degrees, aluminum really isn't good because it can oxidize and ultimately melt or oxidize. So above 500 degrees, sample pans might be made of quartz, alumina, gold, graphite, etc. In terms of the reference material that in DSC applications, that reference material is almost always just an empty sample pan. You want the reference to be similar in its heat capacity to the sample itself. Now, obviously, the sample itself will contain the sample that you put in the pan, but a bulk of that weight will actually be the sample pan itself. So you typically use the exact same sample pan as the reference that you use to place your sample in. And then you can also use different purge gases in the DSC sample holder, nitrogen, oxygen, air, and so forth, just like you do TGA. Most DSC is actually done in nitrogen because you're really looking at phase transformations, not reactions. So you typically want to do it in an as inert environment as you can. You always do want to understand the mass of the sample, the pan, and the lid before and after you do a run so that additional information can be used. Plus, understanding the sample mass before it goes in allows you to do things like calculate specific heats and so forth. This slide appears to basically have the same information that we talked about in the previous slide, that the reference sample should basically be similar to the sample itself, so you can read this slide on your own. When trying to interpret a DSC curve, our objective is to correlate the features with the actual thermal event taking place in the sample. After some kind of a baseline correction, the peak area itself is actually proportional to the actual enthalpy change, right? So we can relate delta H, or the enthalpy change, to the area of the peak times some kind of a constant and divide it by the mass of the sample. That constant can be obtained by melting a known amount of a pure metal. And then here's just a list of recommended standard materials for actually, calibrating a DSC, and you can go through and look at these. In my lab, I actually use indium as a calibration metal. My DSC only goes up to 400 degrees because most of my customers are pharmaceutical customers. DSCs do go to higher temp, but for my application, indium's a good use. Reversibility can also be checked on a DSC. So here's an example of some kind of a crystallized polymer. Note on this particular DSC plot, it is indicated exotherm up, endotherm down. dQ or delta Q being the heat, or the change in the heat. So we have an initial heating of the polymer, right, which shows up as a TG. So there's the TG on the initial heating, followed by an exothermic event. So that's going to be crystallization, followed by a melting event over here. Okay, now we're at a liquid in this case. Sorry about all the clicking if this is getting recorded. And ultimately, if we get high enough, it decomposes. Obviously, if we were to stop the heating and then just stop it and turn it around and go into a cooling process, at some point we'll get, either crystallization or melting. And in this particular case, we're going to go from melting to a crystallization at this point here. So this is just an example of the heating and cooling curve for a partially crystallized polymer. The conclusions drawn from a DSC trace should probably be corroborated with some other technique. You can kind of try to figure out this table. I think it's kind of self-explanatory. If you have a melting events, something like hot stage microscopy could use to actually observe that melting event occurring at a particular temperature. If you have dehydration or decomposition, you might be able to check it with X-ray diffraction. If you've crystallized something or actually changed the structure of it, so maybe you've gone from one crystal type to another crystal type, X-ray diffraction could be used to check that, and so forth. I mean, I think this slide is fairly self-explanatory. Now we talk a little bit about the measuring of heat capacity. So an important benefit of DSC is that you actually can measure the heat capacity. Delta H can be written as the sum across the temperature range of the heat capacity of the material times the change in temperature. Correspondingly, the change in entropy can be written by substituting in where delta G is 0, then delta H equals the temperature times delta S. So you can substitute T delta S for delta H, bring the temperature underneath, and you get delta S is the integral from T1 to T2 of the heat capacity over the temperature times the change in temperature. So when a sample is first introduced, the DSC baseline is displaced in an endothermic direction. That's because you've actually added sample to the sample pan, and you're relating it to another sample pan. And that displacement is some value H and is proportional to the total heat capacity. So by adding some mass of a sample to a sample pan, you've increased the heat capacity overall. And that shows up as a displacement H between a pan only and the pan and the sample. That H value is proportional to Cp, and H is equal to some calibration factor B times the heating rate times the heat capacity of the material. So the value of B can actually be determined by heating some kind of a standard that you know the heat capacity of. Sapphire is what's typically used. It's what I use in my lab. So you would run that same sample with sapphire, and you would relate the area of the curve for your sample relative to the area of the curve to the standard, and back calculate that constant B, and then calculate your heat capacity. The measurement of thermal conductivity, I'm going to skip this. I mean, it's not something I've ever actually done. It's actually done by putting a probe at the bottom of the sample and a probe at the top of the sample and measuring the heat between, you know, the bottom part and the top part, but I'm not going to talk about it. So DSC can be used to determine phase diagrams. So represented in front of us is just a kind of a standard phase diagram of two components, right? With a liquidus region up in the top, and then you have a component that's liquid plus B, you have a component that's liquid plus A, and then we have, you know, a combined solid solution of A and B in the bottom rectangle. Obviously, the melting point for pure A or pure B, which would be these, can be directly measured by running a DSC curve on examples of, you know, pure compound B and pure compound A. On the following slide, and you may need to flip back and forth. I don't think I can kind of go back and forth when I'm recording or narrating these slides. But if you go to the left side of the previous plot, you'll see TA and TB by going back and forth on the slides. You'll see that TA is up on the upper left side of the plot, all right? And as you move down at that temperature for the particular mixture at hand, you reach that TB point, all right? So in this particular plot we have, this is actually a DSC curve for the slow cooling of the mixture, so be careful about that, slow cooling. So what that basically means is we're going from high temp to low temp, decreasing temperature. So in this side, we're a liquid, all liquid. At this temp, this is the temperature at which B solidifies. Sorry about the clicking. And so that's why this says endotherm up, because you're cooling, so just beware. So this is actually the crystallization event of the B portion of the solid, and then you get to TE, and of course this is where A solidifies, and so you have A and B is solid. Wow, this is terrible. Anyway, you get the picture. So this is how you could develop a phase diagram using melting points of pure materials and then doing cooling curves from the liquid. But like I said, toggle back and forth and you should be able to relate TA, TB, and TE to the previous graph. And hopefully this makes sense. If heating is done instead of the cooling, the curve should ideally be an endothermic mirror image of that shown. And so what you basically could do is do a series of curves at different mole fractions, and then you can just basically see these are the exothermic events, and they should tie back to the phase diagram. Now we'll talk a little bit about some general applications. You can measure the temperature and enthalpy changes for specific thermal events. In general, the enthalpy is proportional to the area of any of the peaks after your baseline correction. Shown down below in the DSC plot, which is endotherm up, we have the same example that we had with TGA, and the corresponding TG curve is shown there on the right, framed in blue, of the copper sulfate pentahydrate. And you can see the first an endothermic event, and it's endothermic because you're actually losing water. So you're changing the structure, but you're not crystallizing from a liquid. So we're not decreasing the entropy in this case. But so it's an endothermic event where we're going from the pentahydrate to the trihydrate. You can measure the enthalpy by roughly measuring the area of that peak. And as you can see, the approximate area of those peaks is probably getting smaller as you go from trihydrate to monohydrate to copper sulfate. And then you can see by looking at the corresponding TG curves that the approximate temperatures where these transitions occur does correspond to the TG curve. But the point is you can actually measure the enthalpy changes for these specific thermal events as we lose the hydration state for the copper sulfate. So here's an example of a solids to solid phase transition without actually losing or having any kind of a reaction going on, and the measurement of delta H for these transitions. So in this particular case, we have carbon tetrachloride, which is below 0 to be a solid, and it's endothermic up. So as we go from a monoclinic to rhombohedral to cubic to liquid, you can calculate the delta H for each one of these transitions. And then a great use of DSC, and it's probably the most common use of DSC, aside from maybe pharmaceuticals, is in the study of polymers. Most polymers are actually formed by creating a melt and then rapidly cooling it to some low temperature, quenching it, thus freezing it in a glassy state. By taking a sample like this and heating it above TG, we get a glass transition. So there's a change in the specific heat, but there's no actual change in the enthalpy. So we don't actually get a peak, we just get what's effectively a change in the baseline. Then as we continue to increase the temp, we actually get crystallization at some point when it goes from an amorphous state, and so we get an exotherm, followed ultimately by melting, which is the endothermic event up, and then followed ultimately by oxidation of the polymer and then degradation of the polymer. And then of course the top bullet on this slide relates to the last the last plot. So the degradation and oxidation of polymers can be studied in DSC. So that's where you you actually get a change in specific heat, but you don't actually get a change in the enthalpy. For recycling plastics, identification is important, and here's just an example of using a DSC curve to provide a fingerprint of materials. So you may have a mixed plastic, you could run a DSC, and then you could identify each of the melting points of the various polymers.